Hello and welcome to an ofxATK tutorial. Today we will be discussing how to receive MIDI input in an openFrameworks project. As usual, go to the project generator, give your project a name. We will be using ofxATK and ofxMIDI in this tutorial. I'll have a link to both in the description. And generate your project. Okay, so first let's go ahead and get rid of all of these extra commands. We will not be using them in this tutorial. Let's add include ofxATK.hpp and include ofxMIDI.h. If we delete these functions here, we have to delete them in the CPP. And this is just to simplify our code here. We should be left with setup, update, and draw. Let's also go ahead and change the screen size. We won't be using any GUI or any graphics whatsoever in this tutorial. We'll just be using the MIDI controller. So let's make it something a little less invasive. I'll be making it a 200 by 200 square. And let's just add our boilerplate audio function. So we'll need an exit function and a sound out function. Audio out. We'll go ahead and add these to our CPP. We might as well go ahead and add the for loop. Make a current sample, set it equal to 0, and fill the buffer with those zeros. Add our left sample and our right sample. This will be a monophonic synth, so these will be the same value throughout. Go ahead and add your exit function. And here we'll need to close the sound stream. We can't close it if it's not open, so in our setup function at the very end, add of sound stream setup. 2 output channels, 0 input channels. We will use the sample rate from ofxATK. That way the library and your project remain the same. And 4 buffers. At this point, if we try to run this application, we should have no compile errors and hear nothing. We can run this in debug mode. Success. Okay, so for MIDI, we'll need to do something we haven't had to do for any other add-on, and that's extend the MIDI listener class, or have our class of app inherit from the MIDI listener class. So without knowing it, perhaps, we've always been inheriting from of base app or openFrameworks base application. This class contains everything our basic application will need, and we can actually look into that if we'd like. Jump to definition. If you're on Xcode, this could take a minute. There we are. So here's our class of base app, and that class is actually inheriting from both of base sound input and of base sound output, which is where we get our audio thread from. You can see here we have a bunch of virtual functions: setup, update, draw, exit. So that's how the code automatically knows what we mean when we make these in our project. You can see a lot of familiar callbacks here. So we've been inheriting all along, whether or not we've known it. Okay, so C++ is special in that you can do multiple inheritance. So we're inheriting from base application. We can also inherit, we'll give it public access, from ofxMIDI listener, which is a class in ofxMIDI. This will allow us to use the following function. Void new MIDI message. This will take the type ofxMIDI message. So now we have a function that will be called every time the application detects MIDI input. So let's go ahead and make this in the CPP. I'll put this just after the audio function. Void of app new MIDI message. And there we go. So every time we have a new MIDI input, whatever code we put in here will be called. Okay, so we have a number of ports, 16. We need to find out which port we'll need to open. So the easiest way to do that with this library is to first make a MIDI in class. So ofxMIDI in is the name of the class, and we can call our object MIDI in. In our setup loop, or function I should say, if we call MIDI in.list ports, this will list all of our MIDI devices in the console window. So if we run our application, and we've spelled everything correctly, we should have a nothing on the actual window, but a list of our MIDI devices in the console with their respective port names, numbers. Here we are. So I'm going to use port 3, which is my physical MIDI controller. Just look through this and decide what you need. So to open that port, we simply have to write MIDI in.open port. I'll use port 3. So the port is now open. And we'll need to add assign a listener. So MIDI in.add listener. And we need to tell it what to listen to, and that will be this, which is of app. So now what we've done is told the application to listen, and if we get something, call this function. So let's go ahead and add something here that we can use to verify that it's working. Let's print to the console, cout, and we can print, let's just go ahead and print the elapsed time of the application. That should be simple. So of elapsed time f inline. So anytime I provide any input from the MIDI controller, we should see how long the application's been open, printing in the console. So I have a small max patch here just to show what my MIDI inputs are. This is not connected in any way to the application. Oh, get elapsed time, my mistake. So of get elapsed time f. Back to this though. If I provide MIDI input, you'll see it here. This avoids the need of a webcam or something like that. So I have the leftmost is my pitch wheel, 2 CC knobs, and notes. All right, so notice when I press a key, we get the elapsed time. When I hold the key down, we're actually not sending any continuous signal. It won't get another signal until I let the note off. And note, that is an important distinction here. Note off messages aren't really special. They're just a note message with the velocity of 0. So a note on is any velocity other than 0, which can be a 0 to 1 or 1 to 127 for a note on. The velocity is how hard you hit the note. Okay, so moving right along, let's print something a little more meaningful. Let's go ahead and print the frequency that we'd expect from a given note. So if we write message, which message is going to be, it's a specific data type for ofxMIDI that contains all the information of the MIDI input we just delivered. So if I do message.pitch, this will give us from 0 to 127 the pitch we just gave. And notice those pitch isn't exactly the term I would like to use. That's more of a note number. We'd have to assign a frequency value based on our 0 to 127 value. Fortunately, we have a function called m2f provided by ofxATK that will convert our MIDI number to a frequency value. All right, so we can just write cout end line. And just like that, we have frequencies being delivered anytime we hit a new note. So if I hit C, we have 130 hertz. We should have around 260 for this next octave. Correct. Okay, so that's working fine. Let's listen to this. We'll use a wavetable oscillator. I'm going to use a triangle wave. So wavetable triangle. I will just call it triangle. Let's give it a starting frequency. Of 200 hertz. And then anytime we have a new MIDI message or a new MIDI note, we will assign the frequency to that wavetable triangle. So triangle dot set freq m2f message dot pitch. All right, so this is not in our audio thread yet, so let's adapt that. We'll have to process that oscillator every sample, so triangle dot process, and we'll assign our current sample to triangle dot get sample. And the line I'm about to add is necessary for Soundflower, I've discovered, which is how I'm routing the output audio to the video. Feel free not to add this line, but I'm going to do current sample. I'm just going to scale that down a bit. Previous tutorials, the audio is clipped going through, even though it's never exceeded -1 to 1. For some region in this conversion, it does not get scaled right, so I like to give myself plenty of headroom here. Let's go ahead and run that and see what we're left with. Okay, so we have a triangle wave. It's at 200 hertz, presumably. I'll hold down C. I'll play a C major scale. Just like that. However, you might suspect we have an issue. I'll hold down F, then I'll play a C. Now watch what happens when I release F. It got a new message value with that frequency. Watch it. When I release C, the pitch will go back to C. So even though those were note off messages, they were still registering. So this needs to be put into a condition. ofxMIDI makes this very clear. If message.status equals MIDI note on, then we'll set the pitch. So this will only set the frequency if it's a note on message, which means it will only set the frequency if the velocity is greater than 0. so now we have continuous frequency. It'd be nice to have distinct notes instead of just changing the frequency. So to accomplish this, let's add an envelope. We can use a constant time envelope as opposed to a constant rate. Simply call it envelope. Let's construct it. For each sample, we'll have to process the envelope. And now, instead of just getting the sample, we'll multiply the sample by the envelope. So envelope dot get value. Okay, so now when we start, we should hear nothing. The envelope is set to non-triggered at the beginning. So when we do get a new note, we will need to set the envelope on. Set gate to 1. All right, and so if we're turning the envelope on, we'll need a way to turn it off. So let's go ahead, else if message.status equals MIDI note off. And then we can simply write envelope dot set gate 0 for off. Helps to spell things correctly. All right, it's successfully compiled despite what it seems to think. Let's see what we have. It started with no sound because it's multiplying by 0. So if I hold F, we get an F. I let go, we no longer have an F. Okay, great. So you might think we have a problem though. So if I hold down an F, then I hold down a C, what happens if I let go of the F? I still have that most recent note held down, but the off gate triggered our envelope off. So we'll need to add a condition to only turn the envelope off if it's on the most recent note. So if the velocity 0 is 0 of a note, only turn the envelope off if that was the most recent pitch or the most recent MIDI note. So to do this, we'll simply keep track of the most recent note. And there's no reason to name this anything confusing. Recent note. All right, so when we get a note on, we will set that most recent note equal to message dot pitch. So 0 to 127. All right, so if we have a note off, we have to add another condition. If message dot pitch is equal to most recent note, then we can set the gate off. Okay. So I'll hold down an F, then I'll hold down a C. Now when I lift the F, it shouldn't stop the note. We'll try it again. Hold down the F, then hold down the C. Then I'll let go of the F. It did not stop the note. So we have success there. Okay, so let's add the pitch wheel. The pitch bend wheel is special. Most MIDI values are 0 to 127. That's because it's 7 bits. The pitch wheel uses 2 messages, so that's going to be a 14-bit value. So we can write else if message.status is equal to MIDI pitch bend. So if our message from MIDI is a pitch bend message, then we'll need to adjust the pitch of the oscillator based on the amount of change in the pitch bend wheel. So notice, if you're familiar with physical MIDI keyboards, the pitch wheel, the bend wheel, always rests in the middle. You can pull it, but when you move your hand, it goes back to the center. We want that center to mean that the pitch is unchanged. For this example, we'll go up an octave if the pitch wheel is at the bend wheel is at the max, and if the down an octave if the pitch bend is at the lowest point. Okay, so we'll have to think about how to accomplish this. So I'm going to write float octave equal of map. So let's map the message dot value, which it's 14 bits. So if I'm not mistaken, that's 0 to 1600 383. 0, but I believe ofxMIDI has that stored for us. So MIDI max bend, correct. So from 0 to the maximum bend value, and let's map that down an octave, we'll call -1, and then up an octave, which is 1.0. And then in the center of that, we'll have 0, which will signify no change. So frequency is non-linear, so we need to adjust for this. To do that, we can make our scalar value. We'll call this frequency scalar. And this will be the power of 2 to the octave. So let's just think about that math quickly. If we have all the way down, -1, 2 to the negative first power is 0.5. So we'd be multiplying our frequency by 0.5, which will put it down an octave. 2 to the first power is 2. So we'd be taking our current frequency value and multiplying that by 2, which takes it up an octave. So this works well. So we just need to triangle dot set frequency. This will be our most recent note. So MIDI 2 frequency, most recent note. So that's our current pitch times our frequency scalar. And that should do it. All right, so I'll hold down C. I'll try to go down an octave, back up, and then up an octave. All right, what happens if I put the pitch wheel all the way down and then start a C? It didn't play the C that was down an octave. Watch if I just move the pitch wheel a little bit, it just jumps. So when we have a new note message, we'll have to make sure it takes the frequency scalar value into account. We can't just, what we'd like to do is when we set the frequency, multiply that by frequency scalar. However, this variable, freq scalar, is out of scope. We make that variable here, so this cannot use it. What we can do to simplify that, or to fix this, make this a locally global variable. So float frequency scalar, and then we'll get rid of this float here, so we don't need to remake that. All right, so when this application runs, it's going, at least in this compiler, it will assume that value to be a 0 since we did not instantiate it. So let's fix that. Frequency scalar will start as 1, which will be no change. It'll multiply this frequency by 1, keeping it the same. So let's make sure this fixed our problem. I'll hold down, I'll put the pitch wheel at the lowest position and play the C. And it played it at the correct octave this time. put the pitch wheel down, play an F, bring it up. Great. So now let's add one of our CC knobs. You can use a slider, doesn't matter. And assign that to a master volume. We will need to know the control number of the knob we want to assign. So let's see out message.control. Now when we run the application, if we move a knob, we can find out what control number that knob is. I'm moving a knob and the control number is 20. So whatever number you want to assign, just remember that. And then we can add a switch statement to make it easy to add multiple. We'll switch based on the message.control value. Mine was 20, so if it's 20, we'll need to do something here. Then break. And then I'm going to add a default, so if it doesn't match any of these conditions, see out message.control. Then I'll add a little note, not assigned. So this will report the control number and then tell me that that control number is not assigned. Okay, so let's make a global amplitude value. Global amplitude. At the beginning, we can set this to something like 0.7 seems reasonable. And then at the end, remember, you might not have this variable. This is just for my screen recording software. But current sample times equals global amplitude. So that will happen every sample. And here we can assign that global amplitude value. So our message.value, if we're at the control number 20, we'll set our global amplitude equal to this divided by 127. Remember that this value will come in from 0 to 127. So if you divide it by 127 as a float, then we'll get 0 to 1 as our global amplitude range. Or we might not. It's almost always a spelling issue with me. Great, so that works. Okay, so one thing we might consider, I did add a second knob here, which is not assigned. So let's go ahead and assign that. Let's add a Portamento feature to this. So our frequency, we'll store that as a smooth value. Frequency. Smooth values are typically used to smooth the transition from one thread to another. So it's a low pass filter that you assign a period for. So we can use this as a Portamento, which will be a nice way to abuse this. So let's go to our setup. We'll say frequency, which is our smooth value data type. Set that smoother to be a new parameter smoother with a starting time of 100 milliseconds. We'll set the frequency target target value, set that equal to the frequency current value, which will also set equal to 200 when the program starts. Okay, so for the smoother, we need to update this every sample. So our frequency current value is equal to our frequency smoother process the target value. And then after we set our current value, we'll set the frequency of our triangle oscillator to that value. Set frequency to frequency.current value. And this should look a lot tidier once Xcode catches up. Okay, so instead of directly setting the frequency here, we'll just need to set the target frequency. So frequency.target value. And we also set the frequency in the pitch bin function. So frequency.target value equal to this. And let's go ahead and run the program just to make sure that didn't break anything. It did. I bet I spelled something wrong. Ah, didn't spell it wrong, I just added it unnecessarily. The function is setFreq, not setFrequency. So now we should have a slight ramp between frequencies. So I'll hold an F. Okay, great. So let's use this second knob to change that time, to change the time of the Portamento. So simply add case 21 frequency dot smoother set time, and let's map 0 to 127 to something reasonable. So of map message dot value, if we're on control number 21, from 0 to 127, the original range, to let's do 50 milliseconds to 1.5 seconds, so 1500 milliseconds. Great. Okay, that about sums it up. So this is a monophonic synth. Polyphony is a much more difficult challenge, in my opinion, especially in C++. So that's what we'll be covering on the next tutorial. I hope this has been helpful for you. Thank you.